the beginning. Okay. Thank you for inviting me and my team to present the paper extrapolating the experimental data to predict the longevity of the Li-ion battery. And first of all, I want to introduce what is the Li-ion battery, because today we should focus on the computer science and the technology. I just want to mention that using low-cost expenditure and low-carbon Li-ion batteries, in short form LiPs, is a key avenue to face up with the increasing number of climate problems and energy crises on a global basis. To be specific, the prediction and extension of the longevity of Li-ion cells are highlighted. We want to say that we do a lot of research on previous works. I will give it a subtitle, Stood on the Shoulders of the Giants. First paper I want to introduce is made by Severson et al., the MIT team. They use the variance or the change in discharge voltage to measure the cycle life and forecast the life end in response to the cycle. They split the data into the transient primary test and the secondary test to get very good result. Let's look at the table. Okay, the RMSE is the rooted mean squared errors, especially in the discharged model. They've got 91 cycles in the primary test and 173 in the secondary test, with a very low mean percentage error in the prediction. For example, here 13.0 in the parentheses, that is 10.1, that is the result after optimization. And here after classification, the first primary test is not that satisfactory. You can see the result is only 78.6%. However, after optimization upscale, the result has been greatly improved to 97.5% in the secondary test. In the next graph or illustration, you will see a lot of lines. These are the discharge capacity in the unit of AHN in response to the cycle number of the cell. Actually, here it should be 124 cells. One thing I want you to pay attention to is the initial speed of this discharge capacity, because in our common sense, the cell should have a declining behavior in or during its discharge process. However, if you watch closely, you notice that the trend is not declining. Instead, it's increasing. So that's why we need to classify the initial speed into increasing one and decreasing one. Okay, next page. Let's look at the paper has been published in the energy. The team is Yang Fangfang et al. They run the data and got very excellent adjusted R-square with 0.998 for the simulated data 1 and 0.997 for the simulated data 2. We can see the table to prove that the result is nearly perfect for the adjusted R-square. Model A is based on the Coulombic efficiency, in short form CV. That is the benchmark, or we say the way to measure whether the energy is efficient or not. Then we can see using the first model, model A, they can get a better result than beta B in terms of RMSE and adjusted R-square. Next, I'm going to introduce the experimental methods and the results from my team. I will use a different way. I noticed that the last team used the first experimental methods and then the experimental results. I may use one layer by another layer, that is one method, one result, another method, another result. But we use the machine learning, include the polynomial nonlinear regression, and the second one, SVM, support vector machine, for the prediction, not for classification, and the multivariate regression. Here, we also integrate a lot of subjects or disciplinary, such as computer science, physics, calculus, statistics, and etc. Here you can see, the picture on the left is more like the waterfall, but it's in a non-linear shape or non-linear morphology. Therefore, we plan to use or build a model of polynomial regression with the degree equal to 2. Here we have a statistic method, that is R-square, to help us measure the goodness of the fit level. But you know that R-square is very hard to calculate. We need to measure the proportion of the unexplained variable to the total errors. So we use the code in Python and programming to help us solve this problem. We can easily get the result of R-square and adjusted R-square. And normally, the usually adjusted one is smaller than the R-square. And after that, we found a very interesting relationship between value A, that is the acceleration rate of the degradation of discharge capacity, and B value, that is the initial speed of the degradation. As I said before, one case is that the initial speed is decreasing. That is, that corresponds to our common sense, or we say within our imagination. Therefore, we say B is less than 0. But in another case, the initial speed is increasing, then we classify it as B is greater than 0. We use the embedded loops and the iteration, aggregate number of accuracy and put it into the accuracy set with capital letter A. Finally, we get the result, as I said before, the actual result in the second column, predict volume value in the third volume. And finally, we got the accuracy ranging from 93.253% to 99.725%. In order to validate and verify whether the regression of statistic analysis is sound and effective, we use another way to prove that. That is calculus and the geometry. Here we have I need to explain what is this XY coordinate is about. D of X actually is the polynomial we set up with just look like the quadratic function, but with the epsilon at the end that represents the minor error. And d prime of x is just the initial speed. We can use the first derivative to calculate that. It's not that difficult. And the second derivative, we say double prime, is the acceleration, that is 2 into a. According to the algebra, we can calculate the number of the discharge capacity. And then I will show you how we can measure the number of discharge capacity according to the geometric area. Here you see the orange line, which starts with a positive number. That is when the initial speed is increasing, or a positive sign. Then we can notice that the area is more like a triangle above the x-axis, and there is another triangle under, below x-axis. We'll cancel out these two geometric area, and the negative geometric area begins from this point. This is a very small trapezoid. We can calculate this area because according to our data, we know what is the length of this side and the height. And when this line move forward, that is when the initial speed is a negative sign, then we can have a larger area of the trapezoid. Then we equalize the from the left side, that is the algebra derivative, and from the right side, that is the integral of the area of the trapezoid, as I written here. Then finally, by using the code in Python, we got the relationship between A and B. We ignore the very minuscule part. We only leave the 1.37 left, and we keep it left, excuse me. And we finally find there is an interesting relationship, or say a multiple relationship between A and B, regardless of very small particle at the granularity level. And we also want to prove that the regression analysis is correct when we use the numeral relationship or multiple relationship to run the data and get the value of A, and finally we have the polynomial regression model. Here you can see on the upper side there is a graph from the laboratory. In this graph, we can see some experimental errors in the very beginning and in the end. In between, you can see some outliers flying up. We guess from this point, we call it critical point, there is dramatic decrease. From this point on, there is an immediate exacerbating decline. And from this point, that is the next stage. We regard the degrading process of the battery as the heartbeat of a person. Therefore, we use this video to show you. And we calculate the first derivative of CV and the acceleration derivative of it. Finally, we have this picture. Next one, I want to show you the non-linear regression. In the first part, we can see when B is less than 0, that is a declining initial speed. And the second set of illustration shows when the initial speed goes up. And finally, we got the result that is general accuracy is 74.081. It is not that satisfactory. Therefore, we use the classification to augment our model. Then we got a comparatively higher results in terms of accuracy percentage, around 97.5. And we found that all the numbers comparatively, we say generally normal distributed as we expect. And then we use the other two models to predict or forecast the longevity of the cells. The first one is SVM. We use the 3D to illustrate how we do that and with the color spectrum. Finally, we got a comparatively good result in accuracy percentage. To our amazement, the R-square and adjusted R-square have been greatly improved. Okay. Next, we use another model that is multivariate regression. That means we need to use multiple variables to predict the value of the cycle over cell. We choose 3 factors or features: temperatures, discharge capacity, and energy efficiency. As I said before, C, economic efficiency. We use the statistic method to and code from Python to get a value of a P. We found that these 3 variables or factors are significant in contributing to the prediction result. And another factor, another another important benchmark I want to mention is the DW, the Durbin-Watson. Here, the DW is super small, only 0.184. We do not think it is that possible, that reasonable. So later on, we try to check out what happened in our regression. And there is another problem in our regression. We found that the condition number is too large. It is almost 8,000. This might indicate that there are strong multicollinearity or other numerical problems. So we guess there are some problems in the multivariate regression, not because the coefficient is not that related, but it is because maybe a pair of variables or even three of the variables are correlated to each other. And here I want to explain Durbin-Watson. Durbin-Watson is too small. One possibility is that the sample is too small. And another possibility is that our predicted value is overestimated. Therefore, we do some pictures. We found that at the end of prediction, there is an uptick. The number goes up, the predicted value, a little bit overestimated than we expect. So through this method, we optimize our model to make sure the predicted values goes closer to the actual value. Last but not least, I want to introduce the authors of my paper. So as for me, my name is Jiaotong. I come from Thai's Education and Technology Company, and He Sheng is from Netherland University. And Gao Bo, he is a professor in Beijing Jiaotong University who working in Beijing now. And that is the presentation of my team. If you have any questions, we welcome you to throw it at us.